Yeah? Anyone? Hear me, see me? Yes, no?
Yes, we can say.
Yeah? You can hear me? Okay, okay, great. So, yep. So let's get, and you can see the screen, right? The presentation?
Yeah.
Okay, great, thank you. So we're going to continue. So what we saw is we have this transmon, okay, with its antenna and its dipole moment, and it's coupled to an electromagnetic mode in this cavity. But this is not the only way to couple to an electromagnetic mode. Another way is to do it in a completely planar fashion. What we saw at the beginning is that if you just take an LC circuit, just take an LC circuit or any harmonic oscillator, that plays the role of light, of a cavity mode. And in the same way that you can take a transmon and print it on a circuit, you can also just, if you instead of the Josephson junction, if you just put a linear inductor, then you get a harmonic oscillator. So you can take a circuit, which is a harmonic oscillator, and couple it to. So if you think of, so this is a harmonic oscillator, this is your transmon, you can just couple them like that. So what you're seeing here, this dipole coupled to an electromagnetic field, in the circuit language would be something like this, and you can actually implement it physically. And this is what chips where you're thinking of scaling up and putting many qubits, and we'll discuss that a bit more later, may look like. But for now, what I want you to do is I want you to focus on a single qubit. So this is a chip. This is a 10 millimeter by 10 millimeter piece of silicon. The green metal over here. This is a superconductor. It's actually niobium, not aluminum. And if you zoom in over here in this orange box, so what you can see here, these two shiny, the shiny stuff is basically the reflection from the microscope. This is a microscope image, but you have one line over here. It's kind of like it's a square or a rectangle. Another rectangle over here. That's the capacitor of the transmon. These are the two paddles of the capacitor of the transmon. And over here you can kind of see shining. This is the line where in the middle you have the Josephson junction. So this over here, this is your transmon qubit. Now this line over here, this snake-like black line, that's a harmonic oscillator. It's what is called a Coplanar waveguide cavity. It behaves like an LC oscillator. It's the same thing. If you zoom in on a cross section, what you can see, so the black here is the substrate. Okay, and in the middle there's a line. This is this line that you can see here. So you have superconductor, this over here, a line of superconductor in the middle, and then there's superconductor. So you have electric field going from here to here, from here to here. And the length of this sets your resonance frequency. What you want to think of it as if this is like a rope, where at one end you can drive it. So you're driving the voltage, and it's like this rope that you're swinging. And you get the normal modes of the rope, you can quantize it, and you have a quantized harmonic oscillator. So this snake-like structure is a harmonic oscillator. And what you can see here is basically a qubit that is coupled to a harmonic oscillator. It's the same thing as this cavity, this box with a hole in it, with a qubit inside. Okay, but only here you can see how you can put many of them on one chip. And I'll discuss this a little bit later, but before we do that, I want you to now think about, what we've done this whole course. We've built up into the fact that the simplified model of a dipole, we have our dipole, and it's coupled to the electromagnetic field, and we saw this derivation when we talked about a dipole coupled to a quantized field. So we have our dipole, it's coupled to a field. This is the same system as in cavity QED. The big difference, and I've already mentioned this, between natural atoms and their coupling to light and these artificial atoms is because we can engineer the antennas, and there's a lot of freedom there. You can actually reach very, very large coupling rates, meaning that G over here, this is the same G, this is the vacuum Rabi frequency, okay? The vacuum Rabi frequency for our Rabi model and the James Cummings model can be very, very large. Okay? In these systems, if you remember for cavity QED, you had a qubit with about 50 gigahertz transition frequency, and the cavities were also at that frequency. And the vacuum Rabi frequencies was on the order of tens of kilohertz. Here, in the system, you can get G values of around hundreds of megahertz. You can go up to 10 to the 2, close maybe to 10 to the 3 megahertz. Okay, so this is very, very large values, and that's what, if you remember, either last week or the week before that, the diagram where you can go deep into the strong dispersive regime. So this is the Rabi model, if you remember, that we started with. This is after the rotating wave approximation, exactly the same math that we did before. And then you can take this and do the dispersive approximation, where these are the typical numbers that you would get for such a system. Okay, so for a system of a transmon coupled to a cavity mode, you would have your cavity frequency also sits around the gigahertz. The setup that you see here, the cavity mode, is around 7 gigahertz. The qubit is designed to be around 5 gigahertz. So the difference between them, omega r, omega c minus omega q, here it says omega r, doesn't matter, same thing. The cavity, the difference between the cavity frequency and the qubit frequency is about 2 gigahertz. Where G is on the order of 100 megahertz. So the difference, delta, is a lot larger than G. So we're deep in the dispersive regime. And if we calculate the chi over here, okay, so this is chi. And chi for this system is on the order of megahertz. So it can be some fraction of megahertz, it can be few megahertz. You can design it by designing the length of these paddles over here. You can design G to be anywhere between tens of megahertz to hundreds of megahertz. And then you can design chi. And just to remind you, chi equals G squared over delta. Okay, I think it's there might be a there might be a factor of 2 here, depending on the definition. So this is the dispersive. And to remind you, chi is the difference between the peaks when they're number split. If you remember the energy level diagram of the dispersive regime of the harmonic oscillator, we drew that last time. The frequency. So for the system that you have here, you would have a certain resonance frequency for when the qubit is in the ground state, a certain resonance frequency for the cavity when the qubit is in the excited state, and the qubit would have these number split peaks. This is the qubit transition frequency when the cavity has 0 photons, when it has 1 photon, 2 photon, and so on and so on. So this is the spectrum you expect to find for such a system. Now, the way you control a qubit, so what I want to discuss now is how to control a qubit. And the way you control a qubit well, essentially you want to send resonant light coming right at it, but since the qubit is sitting inside a cavity, the density of states is suppressed. Now, you want this dispersive regime and you want a suppression of density of states. And I might have mentioned it here. Yeah, I wrote, mentioned the Purcell effect. We didn't discuss open quantum systems, but I do want to mention the Purcell effect, something that you should encounter at some point in the future. If you just have an atom in free space, you know that it can decay. It can decay away. If you put it in a cavity, because of this term, if you look at just this Jaynes-Cummings term, you have the swapping of energy at this rate g. If the cavity is an open cavity, as the atom is exchanging energy with the cavity can decay away. And if it's a long-lived atom, once you put it in this cavity, it can exchange energy with the cavity and then decay away through the cavity if the cavity is strongly coupled to the outside. And this is called the Purcell effect, where you're increasing the decay rate of the atom due to the Purcell effect. On the other hand, if you now take the atom and you put it in a cavity and you detune it away from the cavity frequency, like you do in the dispersive regime, now the atom sees a very, very low density of states. It has no states to decay into, basically. The only option it has is through the dispersive interaction with a cavity. So the cavity in the dispersive regime is actually protecting the decay of the atom, the natural emission of the atom, and it's a way to create a longer energy decay times. Okay, so just to mention that. So that relates to the Purcell effect. But it brings me to the second thing, which is the qubit control. And, if your atom is just sitting here in free space, you can just send light at whatever frequency you want to it. If it's sitting inside a cavity, especially if we're in this setup over here, the cavity basically shields it from its own field. So it's hard to get the microwaves or the light at the frequency of the qubit right to that qubit. So what I want to show you now is a little bit of math, showing how you can actually drive the qubit through the cavity. Okay? You can skip this math and think about it. If I just take a strong enough microwave light, something will couple through and something will get in resonantly onto that qubit. And what I've written here is the explicit math behind this. So this is qubit driving through a cavity. And what you can see here, this is the Hamiltonian. This is the drive Hamiltonian. This is just the amplitude of your drive. So this is I as function of t. I is just some number, so as function of t. Cosine omega qt, so we're driving at the transition frequency of the qubit, plus q of t sine omega q t. So this is a cosine and sine term going at the qubit frequency, but since it's being applied to the cavity physically through some coupling pin over here, as you can see, then you're actually driving the cavity field. And the way to see the effect that this has on the qubit itself is, and this is a second motivation why I wanted to show you, because we've used these transformations over and over again just to emphasize how useful they are. We're going to apply our favorite transformation over here, and this is e to the power of g over delta a sigma plus minus a dagger sigma minus. We did this transformation, this was essentially the perturbation to get to the dispersive regime. If you remember, when we moved from the Jaynes-Cummings to the dispersive regime, we'd use this transformation, and we're using it now, only now I'm taking only the lowest order. Okay, that's going to be sufficient for now. And if you apply this transformation onto this drive Hamiltonian, your new Hamiltonian, the new transformed Hamiltonian, is going to be this drive Hamiltonian plus, again, this commutator of eta and HD. And you can see that you get the same drive that you had before. This is the same term over here. It's suppressed by G over delta. Okay, and remember, G over delta is a small number. So you're getting some suppression of your power. But now, your operator is sigma x. Okay, so it's not A dagger plus A, it's transformed, and now it looks like sigma x. Okay, so we have a suppression of our amplitude, and it's operating on sigma x. And now what we're going to do is we're going to go into the qubit frame. Again, we already did this transformation many times. To go into the qubit frame, you just go to frame rotating at the qubit frequency. So something rotating at the qubit frequency is just going to look static. Okay? So we apply U, HU. It's time dependent, so we need this extra term of minus I, U, U dot. And then what we get here is I over 2, doesn't matter, sigma x minus Q over 2 sigma y. I think I have a mistake. I'm missing here a factor of G over delta. So apologize for that. Add in your notes G over delta. So there should be like a G over delta factor over this because it needs to suppress it. But what you can see from here, the essential thing is that you have sigma x and sigma y depending upon what you put I and Q. Okay, so you have the two quadratures of the field that you're applying, and I term will give us rotations around the x-axis, and the Q term will give us rotations around the y-axis. So this is just like in NMR. Okay, if you remember NMR, this is exactly the same as NMR. And this control gives us, and this gives us basically full control over a block sphere. Okay, the way it looks like in a lab is like so. So this is what a lab setup looks like. This is a bunch of microwave. This is a bunch of microwave generators over here. And what you can see here in Zoom, this is a mixer. A mixer is just a ring of diodes. The same mixer I explained about when we were talking about NMR. It's the same idea. And it has these 4 ports. One over here, this is the LO. This is where you put your reference frequency, which would be the qubit frequency, for example. Okay. The output of the mixer, RF over here, is just I cosine omega LOT plus Q sine omega LOT. It means that in I and Q, you want to put time-varying voltages, and the time-varying voltages that you will insert into I and Q will give you control over the single qubit in the block sphere exactly according to this equation over here. So if I want to rotate around the x-axis, all I will do is apply for a certain time a voltage on I and then turn it off, and then that will give me a rotation around x. And the same on y. Apply on q. You apply a voltage for a certain time. Typically you would do a Gaussian pulse. It gives a nice spectral width. If you put a box, you would get these satellite frequencies. And so this is how it's done in practice in a lab. Okay? And this also leads me to the second point, and about someone who asked before about the payoff or what you pay in the fact that you use this transmon and you have this low unharmonicity. Who was it that asked before? I don't remember.
I did.
Okay. So this leads me to give basically an example of optimal control. So if this was a tool, if this was really, this is a multi-level system, and in the naive sense, when I did all this derivation over here and all these derivations, note that, I used the operator sigma z. So there's some assumption that I have a two-level system. But our system is not really a two-level system. And if you take these initial calculations, you would assume that if you just take a simple Gaussian pulse, or just turn on and off the I, you would get some rotation around the x-axis, and then you can do, for example, a pi pulse. But like you said, you know, if I'm sending a frequency at the resonant with 0, 1, what is happening is that I'm also not too far away from the 1, 2 transitions. Now, if you go back to several lectures back, if you have an off-resonant drive, what happens? The Rabi frequency, right? You have your original Rabi frequency plus what goes over here? Anybody remembers? There's the detuning of your drive from your resonance. Okay, so your Rabi frequency is a lot faster. So now you're driving this transition on resonance, but this transition is also being effectively driven only highly off resonant, so it's fastly spinning. So you can think of it in that way. Okay? So there is some effect to that interaction. And if you just take that naive thing and you calculate numerically what happens, and you can see this here in this figure, if you just take a Gaussian pulse that ideally would give you a nice pi pulse, so if you start over here, you want to end up all the way down here on the Bloch sphere. You want to rotate around the x-axis. And if you just apply the naive Gaussian pulse over here, you will actually end up over here on the Bloch sphere. The way you can think of it is that due to this extra level over here, there's a small shift. And in the dynamics on the Bloch sphere, it looks like there's force that is slightly pulling you towards the left over here in this figure. Now, we know our Hamiltonian, okay, and we know that our Hamiltonian has more levels, and you can actually take all this into consideration and be a little bit smarter about it. Okay? And if you're being smarter about it, and this is a nice paper, you know, if someone wants, they can look at it. You can even explain the details of what goes on. That could be a nice 15-minute seminar if someone wants to do that. But it turns out that if on the quadrature, so on Q, over here, this is the red part, if on Q you add the derivative of your Gaussian pulse, you're effectively adding this force in the dynamics on the Bloch sphere. It's not a real force, okay, that counters this drifting effect over here, and you can correct for the pulse like this. Okay? Of course, if you do the pulse very, very, very slow, then there's basically going to be no drift, and then you will do a very, very accurate pulse. But as you make your pulse narrower and narrower in time, faster and faster and faster, this effect will be more and more severe. But as long as it's not too narrow and not too terrible, you can always correct for it by adding this additional signal over here. And this is a really very simple example of a larger field that is called optimal control. It's not specifically just for superconducting qubits. It's used in atoms, in trapped ions also. And it really was originally developed in NMR techniques. So NMR techniques, going 30 years ago, started developing these smarter optimal controls. And this is just an example of it. Are there any questions till now? Anyone?
Can you please explain again what is the difference in this technique?
The difference between what and what?
Between the not using it and using it. What exactly are we doing it?
So you if you want to do a pi pulse, you want to bring your qubit from here all the way down to here. Okay? But you want to do it fast. You can do it very, very slow, right? If you do it very, very slow, then the spectral line of your pulse is going to be very, very narrow. So you're going to be hitting this frequency, and this will not play a role. So you will just be doing a very accurate pi pulse. That's okay if your coherence times are infinite, are very, very long. Okay? But if you're now thinking more practical, you want to do your pulse fast. Why? Even if your coherence times are infinite, you want to do your computation fast. You want it to take 5 minutes and not 5 hours. Okay, if you're thinking of this in terms of a gate. But as you narrow and make your pulse faster, then you get basically everything I discussed in the last 5 minutes, and you get this drift. And it seems like, you know, this is a lost cause. But if you resort to these smarter techniques of optimal control, they can actually correct for that. Okay, up to a certain limit, of course. You can see where, you know, this
what
wouldn't
exactly
work.
is the correction? How do you correct it?
Oh, this is the extra. Can you see over here? So the blue line is what you apply on the I port over here. Q is what you apply on the Q here. See, there's an extra pulse that turns out to be the derivative. See epsilon x over here? This is the pulse that you would naively apply. This is your carrier frequency, the qubit frequency, and this is your Gaussian envelope. Okay? If you now add to it, so you're playing both of these at the same time, okay? The derivative of that, this is the derivative of that. This derivative of that is going to add this extra force. It's not a real force, but so this is what you're doing to correct for that. Okay, and you can numerically calculate these things, or like in the paper they did here, they actually calculated it, this thing, in an analytical way. And this is something that is commonly used all the time. These things.
But you also have to take into account the 0 to 3 and 0 to 4 and the other higher levels, right? So
yes, yeah, but the higher you go, the less it contributes. Okay, yes. So effectively you can take all the way. I think I don't remember how many levels they considered here in this paper.
Okay.
But yeah, the more you can always take more and more corrections as much as you can. I don't know, maybe this is analytically correct for as many levels as you have in the swell. I don't remember. Okay, so that was about qubit control, and you can see that you can drive it directly, you can drive it through the cavity, and you can even use optimal control to correct for imperfections due to the extra levels, basically, of this Transmon. The second thing that I'm going to show you now is qubit measurement. And, well, maybe due to time, I'll just mention quickly about amplification. I won't expand too much about it. But when you're talking about cryogenic systems, and we're talking about very, very small signals, if you take the signal that is sitting at, comes out from 10 millikelvin, the size of the signal is basically h bar omega, right? Your vacuum fluctuations are going to be half h bar omega, and this is the order of magnitude of the signals that you're talking about in these systems. If you want to measure a qubit, you want to get a signal from there all the way up to your classical electronics. And if you take a signal on the order of h bar omega, that's about half a Kelvin. If it just goes up to 300 Kelvin, it gets drowned by 3 orders of magnitude of noise. This is why it's important to amplify all the way down, to amplify your signal and your noise. Of course, you have the quantum noise and some small signal. You want to amplify it way above the noise level that you would get at room temperature. Okay, and if you amplify it way, way above, then you don't lose SNR. So this is a whole section on amplification. Now, if you're interested in amplification and specifically in quantum noise and what it means, and there's a whole very interesting physics around that, I can recommend this reference over here, Quantum Noise and Amplification, Review of Modern Physics. It's a very thorough and very interesting, very pedagogical review about quantum noise. So if that's something that interests you, please go ahead and read. But I'm not going to continue and mention any more about amplifiers. I'll just mention that we have, typically we have quantum limited amplifiers, which means they add the minimum amount of noise. And when you have a signal, it goes to that amplifier such that we don't lose much SNR. Okay. But what I want to talk about, so what I'm going to talk about right now is the qubit measurement itself. Okay, so what I have here in this image is, this is a mock setup, okay, of what a setup might look like when it's inside a refrigerator, and I'm using the setup with you have the transmon here, and it's inside the cavity. And again, consider, you know, we're going to look at these numbers. So cavity would be 7 gigahertz, qubit around 5 gigahertz, and chi is going to be around the megahertz. And our Hamiltonian is the dispersive Hamiltonian over here. And now we want to measure this qubit. And the way we're measuring this qubit, and this is why this is another role that the dispersive Hamiltonian plays here. So the dispersive Hamiltonian plays several roles here. One, we talked about, you know, it helps, I didn't show you how, but I told you that it helps in terms of suppressing the decay through the cavity. You know, the cavity decays the density of state, so that's good for the dispersive Hamiltonian. The second thing is that it gives, and this is really the main and most important point, it gives a very easy way and a simple way of measuring the qubit, the state of the qubit. Now, if you take a cavity, oh, I erased that, I didn't want to erase that. If you measure a harmonic oscillator, if you measure the response of a harmonic oscillator, what it looks like is this. So you have a cavity, and you can measure in two ways. You can either take, so this cavity has some coupling to the outside over here and over here. If you take a microwave signal or a light signal, this could be for an optical cavity, you can either send the signal and look at what is reflected, or you can also look at the signal and look at what is transmitted. Okay, now here I've drawn the reflected phase, but what I want to do is I want to change the discussion a little bit and talk about actually the transmission. It's a little easier to understand. If we have a cavity, and here it is coupled very, very weakly, almost infinitely weakly. So if you look at this drawing over here, so here we have two coupling pins of the cavity to the outside. So imagine that the left pin over here is very, very short, and so there's very, very weak coupling, almost negligent coupling. But on the other side, I can insert as much energy as I want. So I can put a signal as big as I want. Now, if my signal is off resonance, so this is, you know, the resonance frequency. Right now there's just a cavity, no qubit. If my signal is off resonance, then I won't be able to get any power into this cavity. There won't be any coupling. I won't have any ability to drive. So all the power is going to be reflected back. On the other hand, if I'm on resonance, some of the power will couple through. And if the coupling to the outside over here is much stronger than this coupling over here, then the light is going to leak predominantly to this side. Okay, so this is a transmission measurement. You send in very strong light. Most of it is going to be reflected because the coupling here is tiny. Some of it is going to populate the cavity. It's going to create a coherent state. We talked about a coherent state. It's just a cavity drive. And now this coherent state is going to leak out of the cavity. But this is assuming that I was on resonance. Now, let's look back at the system over here. And by the way, this pin here is the weak coupled, and this one over here is going to be the strongly coupled port of the cavity. So the information is leaking out of here. Now, for our qubit in the cavity system, what is happening is this dispersive interaction. Okay? And the dispersive interaction, if you remember, the cavity actually acquires two different resonance frequencies dependent upon the state of the qubit. So you have Fg, this is the frequency of the cavity when the qubit is in the ground state, and there's also the frequency of the cavity when the qubit is in the excited state. So, 0, 1, or ground and excited. Okay? The difference between these is chi. And the way you can measure the qubit, it's not exactly what I've drawn on the presentation, but I think it's simpler to explain it like this. The way you could measure the qubit, or the way you measure the qubit is you send in microwave light at the resonance frequency of one of the transitions. So let's say at the resonance frequency of ground. And then you observe. So observing, how do we observe? We put a little eye with eyelashes over here like that. Okay, so we're observing the other side of the cavity. And if we see light being transmitted, what does that mean? Our qubit is in? Anyone?
The ground state.
Is in the ground state. And if we see no transmission, it means the qubit is in the excited state. Now, what does it mean, no transmission? It doesn't mean we see nothing, right? There's always some noise. But we'll see noise that corresponds to vacuum noise, vacuum fluctuations. And what happens in practices in an experiment is that you send in your signal over here. It transmits or not transmits through the cavity. So this is the blue and the red lines. Okay. It gets amplified and it reaches room temperature. And at room temperature, you demodulate and you digitize the signal that is coming over here, and you see a bunch of noise. So this is the green line. So what's actually happening is that you're reading some voltage, some continuous voltage as function of time. So this is a real readout of a qubit. And this is this green noise over here. And if you average this over a certain enough of time, over enough time, then at some point you're able to distinguish between just the usual noise and some offset value. Okay, so over here in this, what you're seeing here is that there are actually two voltage values. One would correspond, let's say, to the vacuum level, and the other one would correspond to a displaced cavity. Okay, so there being some coherent state coming out over here. Now, if you average for very, very little time, you just see noise. If you average for a longer enough time, then you can actually figure out what is the level, and then you know if your qubit is in 0 or in 1. Okay? And this is how a measurement, a projective measurement on a qubit is done in this system. Okay? Note that after the measurement, what happens to the qubit? Suppose that I stop driving it. What happens to the qubit after the measurement? Think about the Hamiltonian over here. Nothing. Okay? The measurement just causes it to collapse. Okay? So suppose that you started your qubit in a superposition of 0 and 1. You now apply a drive and you look on the other side. If you wait for a long enough time, if you see vacuum, you know that it collapsed into the ground state. If you see some signal, you know that it collapsed into the excited state. Okay? Note that, the eye here can be anything. It doesn't have to be an actual student in the lab looking at the monitor. It just goes to the environment and you have your collapse in measurement. Okay? And if you do this experiment many, many times, then you get statistics. So if you put your qubit in superposition, 50-50 superposition, you repeat this experiment many, many, many times, 50% of the time you will see vacuum, and 50% of the time you will see some signal which corresponds to collapsing into 1 or into 0. So this is how you do your qubit measurement. In terms of physics, there's a lot of physics hidden in this noise over here. Physics of wave of this is, again, whoever this is interesting to. The fact that you use quantum limited amplifiers in the system means that this noise that you're seeing here is not just added thermal noise, but it's actually the 0-point fluctuations. which corresponds to the back action of the measurement, which means that you can trace back from this noise the actual collapse of the wave function. Okay, so that's interesting physics, more fundamental physics beyond what we're discussing here. But just to summarize the last few slides, you know, when we want to read out a qubit, we're sending microwaves around the frequency of the cavity, and we want to control the qubit, we're sending microwaves at the frequency of the qubit itself. And then with this, you can just do regular qubit characterization, you know, so see coherence times, a Ramsey experiment. This is a T1 experiment, which is important. If you look historically over the years, there's been really an exponential growth in coherence times. These are different types of qubits. You can see the Transmon showing up here. Here it's showing up in the 3D cavity. And over here in 2020, it's showing up all the way up here with the 300 microsecond coherence times. And this graph will probably keep growing a little bit more until it somehow saturates, and you need to use cleverer qubits, which are sitting down here to keep this increase. But if you're interested, and you know, this is the reference that I gave before, so you know, you can go read about the historical perspective. But in the last 10 minutes that we have, this is the last thing I'm going to do. I really didn't get to all I wanted to talk about, but I really don't want to miss out on the multi-qubit architecture and how you couple these qubits. So we understand one qubit in a cavity, and I already showed you what a chip looks like. These are images of, this is the IBM chip, this is the Google chip, and what you're seeing here are just the covers, and under the covers basically are the architectures, and the chip, basically their chip looks something like this underneath. And what you already saw is that there are two types of architectures, the 3D one, which I showed you, and you can take more qubits and put more and more into the cavity, but this is good to some limit. This is an experiment done in IBM, for example, where they have 4 qubits sitting in the structure with 5 cavities. But a simpler way of scaling is really putting everything on chip over here. And what you can see, this is a chip, again, this is the 10-qubit chip. Each qubit has its own resonator, so you can think of each qubit has its own readout. So you address each resonator to read out each qubit separately. This is the same as was done here in this 3D architecture. And to couple the qubits, there are several ways of doing it. Over here, for example, in this chip, you can see there's one qubit over here and another one over here. And coupling them is a little snake-like structure, which I already know is a harmonic oscillator. So this structure basically is the same as putting 2 qubits in the same cavity. But now here you have this qubit coupled to this one, but this one is only coupled to this one, and so on and so on. So you can play with these topologies and architecture to build all kinds of qubits. But the way you couple and the way you actually do the gates, there are many, many ways of doing it. This is a partial table that gives several techniques. What I want to do in the last, how long do I have? Yeah, I only have 5 minutes. Is it okay if I steal a few more minutes for this lecture? Or does someone really have to go? Yes, no? Well, no one is answering, so I'll guess it's a yes. I'll run a little late, but I'll try to keep it as short as possible. So what I want to show you is one example for a 2-qubit gate. And you can see in this table here, there's blue and there's red. Blue, T means tunable qubits. So you can take a Transmon and make it frequency tunable. If you remember in cavity QED, you can apply a Stark shift, a static field, and that tunes the frequency of the atom. I will show you now how you can tune the frequency of a Transmon with a magnetic field. It's 2 lines of math. I'll show it on the screen in just a moment. And then I'll show you how, suppose that you have 2 tunable qubits, you can create an an interaction between them. And this you have already seen also in cavity QED. This is why it's going to take basically a minute. Okay, so think about two qubits coupled to the same cavity mode. Okay, so this is the Hamiltonian. And we've seen this again in cavity QED. If you remember the experiment where you had the two atoms and then they were colliding in the cavity, they went through the cavity both at the same time. And when they were in the cavity both at the same time, then their Hamiltonian was basically this Hamiltonian. And in the dispersive regime, if you remember, we had this effective Hamiltonian with this effective coupling term. So we discussed this last time. And basically through the cavity mode, these two artificial atoms, these two qubits, can exchange a quanta. So you want to turn on this Hamiltonian for a fixed amount of time. So think about the two qubits being far away. If the two qubits are far away in frequency, then this whole term over here is suppressed. So this is effectively like these two atoms in cavity QED, they're not in the cavity. Now, if you bring one qubit into resonance with the other qubit, then through the interaction with the cavity, we get this, and we get the swapping interaction. And you wait with this for a certain time, and you get a gate. Now this is one of 15 ways of doing a gate. But it turns out it's a very effective way. Now, the way to tune a qubit, to not leave you hanging, is use what is called the split transmon. If you take your Josephson junction, you split it into a ring with two Josephson junctions, you can go through this calculation over here, and you can see that these two Josephson junctions behave effectively as a single Josephson junction, only that the Josephson energy now depends on the external flux going through this loop. So by applying a magnetic field, a small magnetic field going through this loop, you can tune EJ. And if you remember, the frequency of our qubit is just square root EJ over EC. So you're square root sensitive to this flux. And then your frequency you have, and your EJ is sensitive like cosine of the external flux. So you can tune down the frequency of your qubit as much as you want, and in this way you can bring the two qubits on resonance. There are also very clever methods of doing it without tunable qubits, so they can be fixed far away from each other, and by clever activation of microwaves you can create interactions. These are interesting papers. If someone wants to dig into one of those, I would recommend this one, the cross resonance one. This is the gate that IBM uses in their chips. Google, by the way, uses something that is similar to the mechanism that I explained to you now. The current record holder for fidelity of qubits is from this year actually. It is a 99.9% fidelity for a qubit. And it's basically the same mechanism that I showed you now. The coupler here is a cavity, only it can be tuned in frequency through an addition of a squid, a split qubit over here. Here you have a tunable qubit and a non-tunable qubit. So you put the coupler away, you bring qubit 2 into resonance with qubit 1, and you apply the mechanism that I showed you. So the simplest mechanism to explain also turns out to be the one that so far has given the highest fidelity in gate. Okay, and I apologize that we didn't get to talking about encoding or error correction or scaling up. So I will skip all of this, and I'll just say that it looks a lot of the time in the media like there's a quantum computer coming, and it's like right there across the corner. But in fact, in all fields, this field, trapped ions, whatever, there's a hell of a lot of design work, materials, understanding scaling, understanding how to put more and more qubits, and a lot of theory work required to be done to actually reach, some useful machines that can do something interesting with that. Yeah, and I'll leave you I'll let you ask questions right now. Yeah. Does anyone have any questions? Sorry for running quickly at the end.
When do you predict there will be a useful machine in the future?
I'm not going to go. This is recorded. I'm not going to go on record. Next week. Somewhere between next week and later after that. But yeah, I definitely think this is you know, I work in this and this is what I do. I think this is a very promising platform, but I wouldn't rule out the trapped ions. They're very pristine and nice. They have much bigger scaling issues. We didn't talk about scaling here, but those have much bigger scaling issues. And a very interesting platform, this is what you're going to see the week after that, is the dark horse, the way I think of it currently in this race. So this is the neutral atoms, which seem very promising and I think solved some of the scaling issues of the trapped ion. So those are three very promising platforms. I don't know which one will prevail. You know that the industry leans towards these superconducting qubits because it's fabrication based and it's closer to what the industry knows, but in terms of what is the right way, that's a very, very hard question. And I left out completely photons, which is another crazy idea, but don't rule it out. Any other questions? Okay, so if no other questions, so I hope you enjoyed what I've tried to do in this course. I tried going somewhere between very simple, trying to put in some rigor, and also trying to give you some higher level, which would connect you to more modern stuff. And I hope you enjoyed the next two lectures with Roy Ozeri and Yoav Sagi. They're fantastic speakers, and they're talking really about these top-notch platforms. I will put a copy of this presentation on the website. Also, maybe even more helpful for what I taught today, I put on the Moodle, or I didn't and I will, I forgot, lecture notes, which are taken from summer school lectures given about 10 years ago by Professor Steve Gervin from Yale University. He's a theorist, but he's one of the founders of this field, you can say. And his lectures are fantastic. They're 10 years ago, but they're still, basically everything I told you and all the rigor behind what I told you is sitting in those notes. So please open them up to fill in gaps that I didn't talk about. Okay? And that's it.